Welcome to the deep dive. Today, we're really digging into something specific, a real headache in industry. Amine stress corrosion cracking, Amine SCC.
Yeah, it's a big one, especially if you're working with gas sweetening or hydrocarbon processing. It hits right at the core of keeping your equipment intact.
Absolutely. So we've pulled together the key stuff from API 945 and these E standards, the important sources, to give you a really clear picture of this risk.
Right. Our goal here is to take all that dense engineering information, all the process integrity stuff, and make it, well, understandable and usable for you.
Okay, so let's start at the beginning. What is Amine SCC exactly?
Okay, simply put, it's when steel cracks, specifically carbon steel or low alloy steels. And it happens because of two things acting together: tensile stress, like a pulling force, and contact with a specific liquid in aqueous alkanolamine solution.
That's the stuff used to clean up the gas streams, right? The amine treating.
Exactly. It's the chemical workhorse for pulling out H2S, hydrogen sulfide, and CO2, carbon dioxide. Gets them out of gas and liquid hydrocarbon streams.
Gotcha.
And it's important to know this is a type of alkaline stress corrosion cracking, ASCC. That's the broader category for cracking caused by high pH, alkaline conditions. Amine SCC is just the flavor caused by these specific amine chemicals.
Okay, interesting distinction. So it fits into a bigger family of corrosion problems.
Precisely. Knowing that helps connect the dots later, maybe.
All right, let's break down what makes it happen. You mentioned stress and the amine solution. What are the key factors, the triple threat conditions needed?
Yeah, there are basically three main drivers you need to worry about. First, how high the tensile stress is. Second, the specific type of amine being used. And third, the temperature of the system.
Okay, let's unpack the stress part first. That seems pretty fundamental. Is this stress from, like, the operating pressure inside the pipes and vessels?
That's what you might think initially, but actually, no. Operational stress plays a role, sure, but the real culprit is usually residual stress.
Residual stress.
Yeah.
Meaning stress left over from making the thing.
Exactly. It's stress that gets locked into the metal during fabrication, typically from welding or maybe heavy cold working, that wasn't properly relieved afterwards with heat treatment. The higher that locked-in stress, the more likely cracking becomes, and the faster it can happen.
Okay, so high residual stress is point one. What about the ameriamine type? You see these acronyms all the time: MEA, DEA, MDEA. Do they behave differently here?
Oh, absolutely. That's critical factor number two. MEA, that's monoethanolamine, and DEA diethanolamine are much, much more likely to cause ameriamine SCC.
Why is that? Just more aggressive chemicals?
Essentially, yes. They're primary and secondary amines, structurally speaking, and they're just inherently more reactive and corrosive in this kind of aqueous, high-stress environment. Now, you can still see cracking with MDEA or DAP. Those are tertiary and hindered amines, but it's definitely less common. MEA and DEA are the big ones.
Right. And the third factor, temperature. Usually hotter means faster corrosion, right?
Generally, yes. Increasing the temperature definitely makes ameriamine SCC more likely and more severe. But here's the kicker, the really crucial part.
Uh-oh. There's no real safe low temperature? Cracking has actually been reported all the way down to ambient temperatures, especially with MEA.
Wow, okay, so you can't just assume because it's running cool, you're safe from this specific mechanism.
Not at all. And that fact really drives the prevention strategies we have to use, regardless of the normal operating temp.
This is where it gets really practical for inspections, right? This cracking isn't just random, it shows up in very specific places. Depends heavily on how the steel was treated, you said.
That's exactly right. It comes back to that stress relief, or rather, the lack of it.
Yeah.
The vast majority of amine ACC failures happen right at or very near non-post-weld heat-treated carbon steel welds. We often just say non-PWHT welds.
Because the welding process itself leaves behind those high residual stresses if you don't heat treat it properly afterwards.
Precisely. As the weld cools and contracts, it creates intense localized stress fields.
Yeah.
Without PWHT to relax those stresses, you've basically set the stage perfectly for cracking if the annealing chemistry is right. So if I'm an inspector and I'm looking at a non-PWHT weld in a Corrosion service, where exactly should I be focusing? Is it right in the weld bead itself?
Good question. And this is critical for NDT, for non-destructive testing. The cracks start on the inside surface, the process side. They typically run parallel to the weld, but they're usually not in the weld metal itself, or even right in the heat-affected zone, the HAZ.
Okay, so where then?
They tend to pop up in the zone of highest residual stress, which is actually just outside the visible HAZ, maybe a tenth of an inch or more away, a few millimeters, that band just beyond the metallurgical change from welding.
That's fascinating. The highest risk isn't where the metal changed, but where the stress gradient peaks just beyond it.
Exactly. You often find multiple cracks running parallel to each other along that line. The geometry matters too. Like on a set-on nozzle, you might see cracks radiating outwards, whereas on a set-in nozzle, they'll likely be parallel to the weld fusion line.
Any other weird location clues?
Well, one really telling thing is finding cracks on the inside surface directly opposite where something was welded on the outside, like a bracket or a support ring.
Whoa, just from the stress transferring through the wall.
Yep. Purely residual stress from that external weld causing cracking on the process side. It's powerful evidence that stress is the key driver.
Okay, say we find some crack that looks suspicious. How do we confirm it's actually Amine SEC and not some other type of crack?
Yeah, you need confirmation. That requires taking a sample and looking at it under a microscope metographic analysis. What you're looking for with Amine SCC is that the crack path usually follows the grain boundaries of the steel. We call that intergranular. And often the cracks themselves are filled with dark oxides. Sometimes they branch out a bit too. That whole picture confirms the mechanism.
Okay, intergranular, oxide-filled, got it. Now this brings up something you hear debated. Lean versus rich amine. Which one is worse for SCC? The clean amine going in or the dirty amine coming out?
Right, this is a really important point and maybe a bit counterintuitive. Amine SCC is most often linked with lean amine service.
Really, the clean stuff.
Yes, the lean amine, which is basically the amine mixed with water, ready to absorb more acid gas, that's the prime environment when combined with high stress. It's the aqueous solution that does it. Interestingly, pure undiluted alkanolamine doesn't typically cause this cracking. Needs the water.
So why isn't the rich amine, the stuff loaded with corrosive H2S and CO2, the bigger problem?
It's a bit of a chemical paradox. In systems removing H2S, the H2S in the rich amine actually provides a sort of protective effect. It reacts with the steel surface to form a thin film of iron sulfide, FeS.
Ah, barrier layer.
Exactly. That FeS film can help impede or slow down the amine SCC mechanism. So while rich amine systems aren't totally immune, especially if you have wet H2S corrosion issues happening separately, they're generally less susceptible to this specific amine-driven SCC compared to the lean side.
Okay, that makes sense. Lean service is the main danger zone.
Yeah.
But you mentioned earlier that failures can happen even at low temps, and now we know lean service is the risk. Why then is PWHT basically recommended across the board now, even for cooler lean amine systems? Seems like overkill if the risk is mainly lean.
Good question. That broad recommendation for PWHT everywhere comes down to the risk of transient conditions or short-term upsets. Meaning, even if the normal operation seems safe, you can get brief periods where non-PWHT equipment gets exposed to the perfect storm for cracking. Classic examples are doing a steam out for cleaning or maybe having some amine carry over into downstream equipment that doesn't normally see it.
Ah, so short bursts of the wrong conditions on stressed steel can be enough to start cracks.
Precisely. Those short exposures can hit that non-PWHT steel with wet amine at maybe an elevated temperature from the steam, and boom, you initiate cracks that might grow later. That risk is why the industry basically says, just PWHT everything in Navdean service if you can.
Makes sense. So for folks listening who might have older plants, what kind of equipment is most likely to be non-PWHT carbon steel and vulnerable here?
You're typically looking at equipment built before these standards became really widespread. Things like contactors, absorbers, strippers, maybe filters, regenerators, and the associated heat exchangers, especially the shells or channels, depending on where the amine is. If it's carbon steel, handles amine, and wasn't PWHT, it's potentially at risk.
Right, so let's talk prevention. If that residual stress is the main physical trigger, how do we stop it? What's the fix?
The number one strategy is post-weld heat treatment, PWHT. You heat the equipment or the weld area up to a specific temperature after welding to relieve those locked-in stresses.
Okay, stress relief. That sounds simple enough, but the details probably matter a lot. Is there a specific temperature range we need to hit?
Oh, absolutely critical. You can't just guess or use old procedures. The current recommendations, like in API 945 or NA's SP 0472, specify a minimum PWHT temperature of 1175 degrees Fahrenheit plus or minus 25 degrees. That's 635 Celsius plus or minus 15.
1175 F plus or minus 25. Pretty tight window.
It is. And that needs to be applied carefully, not just for the main fabrication welds, but for any repair welds done later, or even welds for attaching things internally or externally during maintenance. Any new welding needs that proper stress relief.
Okay, PWHT is king. What else can be done? Other layers of defense.
Well, you can obviously upgrade materials in high-risk areas. Using solid stainless steel or maybe clad steel or other resistant alloys eliminates the carbon steel vulnerability.
Pricey, but effective.
Can be. And then there's basic operational discipline. If you do have non-PWHD carbon steel equipment and you need to do work on it, welding, heating, steaming it out, you absolutely must do a thorough water wash first. Get rid of any residual amine chemicals that could cause trouble during the heating.
Good point. Cleanliness prevents nasty surprises. Okay, shifting gears to finding it. Inspection, you said the cracks are tight, often oxide-filled. What NDT methods actually work well?
Right. Finding these can be tricky. Because they're surface breaking, you need techniques sensitive to that. The most effective are usually wet fluorescent magnetic particle testing, or WFMT. Also, alternating current field measurement, ACFM. And certain types of eddy current testing, ECT, can work too.
WFMT, ACFM, ECT. Got it. What's the catch?
The catch is surface prep. You have to clean the surface properly first, usually by grit blasting or similar, to remove any scale or deposit so the method can actually detect the crack opening. Cleanliness is key for detection too.
What about ultrasonics? UT is used everywhere. Can it find Amine SCC?
UT, like standard shear wave UT or the more advanced phased array, PAUT. It's useful, definitely. Mostly for sizing cracks once you know they're there, or for monitoring if they're growing over time.
But not for initial detection.
It can be challenging, especially on existing welds and piping. It's often very difficult for the UT signal to reliably distinguish between an actual amine SEC crack and maybe some small harmless flaw that was already there from when the pipe was made, like lack of fusion or something. The signals can look quite similar, so caution is needed interpreting UT results for this.
Okay, good to know.
Okay.
And are there methods that are basically useless for finding this?
Yeah, definitely. Liquid penetrant testing, PT or dye pen, usually doesn't work well. The cracks are often so tight and filled with oxides that the penetrant just can't get in.
Right.
And radiographic testing, RT or X-ray, is also not effective at all for finding these types of fine, tight cracks. It just won't see them.
Any other techniques worth mentioning?
Well, for monitoring large areas or active systems, acoustic emission testing, AET, can sometimes be used. It listens for the tiny sounds cracks make as they form or grow, so it can help locate active areas.
Okay, it's a comprehensive look. So if we pull it all together.
Yeah, if you boil it down, amine SCC is really a classic materials failure story. It's where specific chemistry, the aqueous amine, meets a very localized high-stress condition, usually leftover residual stress. It's predictable and thankfully largely preventable with the right engineering controls. Primarily, that means getting the PWHT right.
And it's part of that bigger family, the alkaline stress corrosion cracking group.
Exactly. Understanding amine SCC helps you understand things like caustic SCC, which happens in high pH caustic environments. Also, carbonate SCC, even ammonia SCC and steel, they share that fundamental link between stress and an alkaline environment causing intergranular cracking. Similar mechanisms, similar appearance. Often.
So what's the big takeaway for you listening to this? For me, it's realizing that sometimes the most critical failure points aren't where you'd expect. Not necessarily the highest pressure point, but this tiny zone, maybe just a tenth of an inch, barely a few millimeters away from a weld. That's where the peak residual stress lives. And it really drives home how absolutely fundamental some basic engineering practices are. Like getting that PWHT temperature spot on, holding it for the right time. That precision is literally the difference between a plant running smoothly and potentially a catastrophic failure.
Couldn't agree more.
So maybe think about this. What other processes in your world rely just as heavily on getting stress relief absolutely perfect? And how confident are you really that it's being done right every single time? Something to chew on.